Hello. I feel weird that this is a recording. We'll see how this goes. Um, this is a new software that I downloaded, so I'm not sure how much memory it has. This may be a couple different files, but we'll see. I don't think I can share my screen while I'm recording. Um, but I'm gonna look at this problem and try to be as explicit as I can. So this is find the Taylor series for f of x. In this case, f of x equals 8 over x. A equals -2. Yeah, find the Taylor series of this, okay? So this was the one that I specifically said, since we went over one similar to this last time, I think you should try this one out for yourself because noticing patterns is something that will only come with time. At least that's been my experience. So I think that this should be something that you maybe either pause and try to do or pause as I'm doing it in front of you. Okay. So last time we discussed Taylor series versus Maclaurin series. They're basically the same thing, except a very common Taylor series is when you have it centered at 0, meaning this A equals 0. It makes our life a little bit easier. Since that's very common for it to be centered around 0, that is called the Maclaurin series. So if they say the Maclaurin series or the Taylor series with A being 0 or centered at 0, that always means the same thing, those three things that I just said. So we are just going to follow our Taylor series formula. Our Taylor series formula is going to be f of x equals the sum as n equals 0 going to infinity of the nth derivative of x of a. So we are going to plug in whatever our a is. So for a Maclaurin series, our a would equal 0. And then x minus a squared. Whoa, not squared, to the n. That is our formula. I'm just triple checking that that's our formula. Okay. So basically what we need is we are going to need the nth derivative of these things. That's why when we were going through these previously, we were doing just starting off with our derivatives. And then once we start with our derivatives, however many we'll need, the problem will tell us that specifically. Then we are just going to plug in whatever value of a that we have, and then we'll plug it into this whole thing. So since I may be a little limited on space, I'm going to erase this. I'm going to write my derivatives, plug in my derivatives, and we'll see how we do on space. Okay, so let me go back to the problem, because the problem, again, will tell you how far you need to go, basically. Oh, wait, so I digress. Either the problem will tell you go to this term, like the fourth term in the series, or find the Maclaurin series or Taylor series. When they say that generally, that is going to be the one where I prefaced this, where you need to do a couple different ones to see that pattern. Last time we did 4. I think 4 is just a good rule of thumb to be able to see the pattern, because sometimes a pattern won't appear until the third or fourth term. That's what we noticed when we did the ln of 1 plus 5x the last time. We wouldn't have known that there was a factorial if we only did 2 terms. So we are going to do, I think just 4 is a good starting point for that. So I'm just going to do 4. So we're going to do 4. We're going to plug in a equals -2 for each of these, and then we'll plug in our nth derivative, put it over n factorial, and then do just x minus -2 or x plus 2 to the n, and we'll see what patterns show up with that. So I'm going to try to write small, because this doesn't look super small, so I'm going to try to be a little small with my writing so it can all fit on here without me erasing. So to make this a little bit better, we can, or more derivable, I guess is the term, we're going to write it as x to the -1, so we can actually take our derivative of this. So our first derivative is going to be, drop down our -1, -8x to the -2. Our second derivative, you could plug in your values. I kind of like just going down the line, these derivatives, then plug in the values. I kind of like sectioning out this, and that's just how my brain works, but you could go about this in several different methods. -2 times -8 is going to be +16. F to the third derivative is going to be, I think I did this already, yep, -48 to the -4. And then our fourth derivative is going to be positive. I'll triple check this, but I must have done this in the calculator. Just so we don't have anything messed up. I know 16 times 3 equals 48, but I'll just double check. And then 48 times 4 is 192, positive 192, x to the -5. Okie dokie. So, we need to plug all these in. Our Maclaurin series actually starts at 0. So we need... Did that stop recording? I don't think so. Yes, it's still recording. Okay, my computer timed out, so I can't let my computer time out. Okay, so we're actually going to start at the 0th derivative, so we're actually going to need to plug this into this, and this. I'm going to rewrite all of these as fractions. That'll make our plugging in a little bit nicer. There we go. So if I have f of x, or f of -2, not timing out, this is going to be 8 divided by -2, which is -4. And then if we have f prime to the -2, that would be... I didn't even type all this out or write all this out. I'll mental math it. So -2 squared is going to be +4. 8 divided by +4, -8 divided by +4 is going to be -2. F double prime of -2 is going to be 2, 4, 8. -8. 16 divided by -8 is going to be -2. If we go the third derivative, -2. 2, 4, 8, 16. 48 divided by 16, +16 is going to be -3. You already know that math. And then the fourth derivative is going to be 2, 4, 8, 16, 32. -32, 192. I'll double check this one. 192 divided by -2 to the 5, -6. Cool. So there are all of our values. All right. So now I'm going to do my Maclaurin series down here. So it is going to be, I'll write it over here just so we have something to refer to. N equals 0 to infinity, f to the nth derivative of x over n factorial, x minus a to the n. Keep writing 2 there, to the n. Plugged in a. There she is. Okay, so when we start at 0, anything raised to the 0 power is going to be 1. N factorial, or 0 factorial, is also going to be 1. So for our 0th derivative is going to be our original equation with a plugged in. And we are just going to divide by 1 and multiply by 1. So we actually are just going to have -4. Then we have, these are all going to be summed. So these are all going to be plus each other. Then we are going to have our first derivative. So n is going to be 1 for all of these values. So it's going to be our first derivative with a plugged in. So that is going to be -2 over 1 factorial, which is just going to be 1, and then x minus a, so x plus 2 to the 1. Yep. And then we have now n equals 2. So now we're going to say my second derivative with a plugged in. Oh, you emailed me. Thank you. -2 again over 2 factorial times x plus 2 to the 2. So it is nice that our factorial and our denominator and our exponent are always going to match each other. That's just like a good double check that we're not messing anything up here in our terms. So now for our third is going to be, right, 0, 1, 2, 3. So that is going to be -3 over 3 factorial x plus 2 to the 3. Cool. And then plus -6 x plus 2 to the 4 over 4 factorial. Okay, so at least in my adventures with this, simplifying the factorial, because the factorial ends up canceling out with certain things, and then those could be our patterns that we end up noticing. So sometimes it's nice, even though we have a factorial, I think sometimes it's easier to do the cancellation when you have numbers. It makes more sense. Or we could still include this as factorial. It's just we're going to need to cancel more things out when they're variables later when we actually make our Taylor series. So it's honestly up to you which way you go. Depends on which way makes most sense for your brain. I just want to check that you didn't. Okay. So -4 can't really do much there. This is just going to be -2 to the, or times x plus 2. And then we're going to say -2 I'm going to do plus all of these because to me it makes sense, because whenever you have a sum notation, you're going to be adding these things. So we're going to need a negative in our answer if every single term is going to be negative. But I think it makes most sense to just have plus a minus. But that's just me. So this is going to be -2 divided by 2 times 1, which is 2. So that's going to be -1 x plus 2 squared. And then we're going to have plus -3 divided by 3 times 2, which is going to be 6. So that's going to be 3 divided by 6, which is 1/2 x plus 2 to the 3. And then we have -6 divided by 4 times 3 times 2. So that's going to be 4 times 3 is 12. 12 times 2 is 24. So that's going to be 1/4. All right. So whenever we want to make our sum now, we are going to, I think, definitely include an x plus 2 to our n, because nothing is really impacting that, it seems. Oh, this is to the 4. Excuse me. Nothing's really impacting that. If we plug in 0 for n, it turns to 1. 0 or 1 for n, 2 for n, 3 for n, 4 for n. Nothing's really canceling there, so that is just going to be in our answer. Nothing really to include there. Uh, I'm trying to think of how I got this answer. I think I just thought about it in the sense of, and I'm not even sure if it works. We can double check it once it's on the board. But I was confident in the past, so we'll see. But since this is going to turn to 1, and we need something in our denominator, so we can assume something factorial or something to the n, like something's going to be in our denominator, where when we plug in 0, it is going to be 1. But the thing is, we start with a -4. So I just said -4, since that's where we start. And then we start decreasing in value. So we're always going to have a negative, a negative, a negative, a negative. So hence why we have the negative there. In our past ones, if it's consistent in one sign, we just need to have that negative included there. And basically, my denominator is going to get bigger and bigger and bigger. Here my denominator is 1. Here, if we start with 4, my denominator would be 2. And here, my denominator would be 4, because I have 4 divided by 1, which is 4. I'm disincluding the negative right now. 4 divided by 2 is 2. 4 divided by 4 is 4. 4 divided by 16? Wait, 4, 1, 2, 4, 8. I think that's what I noticed. Because we have 4 divided by 1, 4 divided by 2, 4 divided by 4, 4 divided by 8. So we actually are increasing from 1 to 2 to 4 to 8 to 16. And that is our power of 2. 2 to the 1, or 2 to the n. Like 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 3 is, or 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16. So I ended up saying 2 to the n. And if we notice, that works with all of our terms. And that's kind of what I was saying previously, in the sense that it is not an exact mathematical way to kind of get there. And that can be frustrating. And I feel as though this was frustrating for me for the first time that I learned it. Just because I don't know how you explain that to somebody other than you just gotta practice and kind of just notice what the pattern is. So I guess in this sense, simplifying these definitely got us in the right direction, but it's kind of thinking of, you need a very consistent format. You need to go back to the fact of, what are you doing? How are you setting this up? You're setting this up as a sum where you're only going to be changing one number. Our most common things, and again, that's where the practice comes in, is having n as an exponent or a factorial of n. In our last example, here I can push this up on the screen. In our last example, oh, my face, we ended up having n, where, over here, we ended up having x to the n, and we also had an n minus 1 in our factorial, because we ended up having, sorry, it's so mirrored, I don't know where anything is, because we ended up going from like 2 to 2 times 3, so we ended up increasing our thing. So it's kind of just seeing what is likely to happen when you just work with a lot of these series. It is kind of nice that we did so much with all of these series before getting into this, so we understand kind of what common things occur, and having a number raised to an n, and as this increases, our denominator in this instance increases, and just recognizing that pattern. But I understand how this can be a lot to understand. And this, I would say we only had 4s and 2s and 2s and 4s. So that's kind of how we got to the point of having 2 to the power of n. I can't, since this was the last thing basically that we're covering, I can't imagine that on a final she would throw something crazy at you. But there has to be, I haven't gotten to that section in the final review, but there has to be example problems in there as well. So I would recommend doing an example problem definitely before the exam just to get that situated. So yeah, I apologize. This can be tough. So yeah, I would say that those are probably the toughest of the ones that we did because it's just noticing that pattern and that's going to be the most difficult part. So just because I don't know how long that these record and have memory for, so I'm going to send you this one. And then the next video, I'll probably do the next 2 series problems. And then the next video, I'll probably do the 2 graphing problems that we didn't end up doing. I'll probably have to send 2 videos for that because I don't know how to go from recording and then screen recording. Because I can screen record it. That'll be a short video though. I'll show you where to get the formula and then I'll screen record and do Desmos and we can kind of graph. But we did one of those the other day and those weren't hard. So I'm not too concerned about that. But okay. All right. I guess see you in the next video.